Hello everyone. So in the continuation of 5 transistor OTA series, we'll cover the second lecture about the frequency response. Okay. So till a previous video on the frequency response, we have seen that how to write the transfer function, open loop transfer function, then closed loop transfer function. What is your DC gain for that, and what is your 3 dB frequency, and what is a UGB actually. So we have seen these few things. Today we'll explore more and further in this frequency response series of actually this is a particularly I will say the frequency response itself is a series. So in the OTA series, it is going to be a matter of 6, 7, or maybe a 10 videos about the frequency response only. Okay, so let I start with a more top level analysis on the frequency analysis. Okay, so till now we have seen the transfer function, and in general I'll repeat what we have done, and after that we'll continue further. Okay, yeah. So what is transfer function? Actually, I have written this, the h of s in general. If it is an open loop transfer function, then I will write it as an open loop transfer function 1 plus s by omega p1. Okay, so this is any means in general open loop transfer function that I can say, and this is a complete representation for the first order system in the frequency response, where omega p1 is a 3D frequency and AOL is a DC gain. And if we talk about the UGB, then what is the definition of UGB? This h of omega magnitude should be 1. Okay, so it is what? AOL divided by 1 plus omega square by omega p1 square equal to 1. I represented s as j omega, so with the magnitude we can write this like. Okay, so if this is a confusion, don't worry about it. So what we think that usually the first order system omega p1, which is a 3 dB frequency, is much less than the omega UGB. So what approximation can be taken here? Omega by omega p1 square, which is defined at omega equal to omega UGB, okay, is much greater than 1. So it the term inside this root, the one can be avoided here, one can be avoided here, so we can write what? Omega by omega p1 at omega equal to omega UGB, that is equal to 1. So from here what we can find? We can find that omega, sorry, okay. So from here we can write omega UGB equal to AOL times omega P1. So this is general 3 dB frequency times DC gain is equal to omega UGB. And also we can write this thing for the closed loop transfer function that I already written in the previous page. Okay, so now we will start our discussion on frequency response on some top level. Then later I'll go on transistor level. Okay, so top level discussion on frequency response 1S. Okay, so what I mean by the top level, actually, before entering into at the transistor level, you will see that what I started with the for the 5 transistor OTA, I started with it is a GM cell. Okay, so for that GM cell, we'll explore the concept of frequency response. So my 5 transistor OTA is nothing but a GM cell whose inputs are like two inputs are there, and I will say that this is your input V in, which is nothing but a difference of the voltages V positive and minus. So here we are getting some sort of current. This current is nothing but Gm times V in, and when this current is fed into this load CL, which is nothing but a mm, is a output capacitance of this GM cell, or can say load capacitance, the second stage load or whatever the stages we are driving with this GM cell. So it is a load. So basically this is a general structure for the GM cell, and from here we'll discuss how to write this transfer function equation and what is exactly this contribution of your this load capacitance. Okay, so what we will see that any op amp, this op amp, the single stage op amp is nothing but a single GM cell op amp. It is a GM cell. It is a GM cell which is generating a current quantity, which is generating a current and giving voltage at output after integrating this current using load cap. Okay, so in general, single stage op amp is nothing but a GM cell only, which is generating a current quantity. And when we integrate this current quantity using the CL, or because in a general network there are two integrating element, whether inductor or a capacitor, but usually on IC design we prefer capacitor for the integration. So the general definition of op amp is nothing but it sends error quantity and integrate it. Okay, so this thing I want to make the point here. So in general, what is the op amp? Op amp is nothing but it takes some quantity that I call V in. So it actually produces some error voltage and then it integrates it. Okay, so the basic thing here is the function integrator. Integration constant is omega u. Okay, so what it does is actually, if this is a beta, so it actually takes your means difference here. If it is used in negative feedback, then we can say it is taking the error voltage and integrating it. So what we can say, this is the op amp structure. Okay, so it is the internal structure of op amp. So first I relate this thing with our op amp, then we'll proceed at the GM cell level. Then this will write the frequency response. Okay, so what is general V out? If I talk about the V out in terms of time domain equation, then V out is nothing but op amp is a device which integrates the error voltage. So I will say it integrates error voltage. So it actually integrates a error voltage, or integration constant is your omega mu. So what I can say in general, it is nothing but omega mu by s times VE is your V out as in time domain. Okay, or in general I can say it takes a difference voltage and integrate it. It takes a difference voltage and for producing the output, it is nothing but V out is A times VD. Okay, so this is general thing. So what I mean to say, it integrates these okay, the error voltage or the difference voltage, then it produces the output. So now let extend this concept to GM cell. Then what is, how we can implement the op amp? Actually, we can implement the op amp. This is my input voltage. So we have a sort of current which is coming through this capacitor and we are generating a voltage. So what is the voltage in time domain? It is nothing but a integration of current across this CL. So it is the integration of current. So what the current? Current is your GM V in dt. Okay. So this V in is nothing but a error voltage I will say, or the difference voltage. So what I can write, GM I will take out, and V in I can write VD dt, difference voltage or error voltage I can write GM by CL times this integration. So if from these two equation, if I compare these two equation, if I call this 1 and this guy I call 2, and what we can see, the integration constant that we have defined in this negative loop system, this integration constant is your what do you call, yeah, omega mu is nothing but GM by CL. So this is nothing but also UGB frequency. UGB frequency. So any integrator, the integration constant is nothing but a UGB only. So it should be as high as possible so that better integration is there. This is a different detail we'll talk it about in some other video. Here the motivation is how to switch these things to the frequency analysis. Okay, yeah. So now this is my GM cell. So ideally what we want a ideal integrator. We want a ideal integrator, which is a concept of single stage op amp or can say GM cell. So what is the current generated here? Current generated here is GMV in. So what is V out? My V out is nothing but integration of GMV in dt. Okay. So now in time domain, this is like that. Now in frequency domain, we can write it as GM by CL, V in S and CL S. Okay. So actually this transfer function we are getting here is GM by CLS. Okay. So now again comment, what is the DC gain? DC gain is infinite. And what is UGB? Your UGB is, let keep this equal to, keep its magnitude equal to, so 1. What is UGB? Omega UGB is GM by CL, that we have already seen on the previous slide. Okay. So two things I got. I got DC gain, which is nothing equal to infinite, and I got UGB. Okay, which is nothing but GM by CL. So from here I can plot this. I can plot Bode plot. Okay. So what is the Bode plot? In general, for the magnitude plot, so it is something like this sort of plot is there. This is a UGB, which I call omega U equal to GM by CL. This is omega, and this is the DC gain is infinite. So I am writing like this. Okay. Now if I come to the phase plot, that what we can see, the phase contributed here is minus 90 continuously. Okay. So let's say this is the phase plot. So yeah, this phase plot is continuously minus 90. Okay. So this is the first order system, and what we can see at any frequency, if this is omega mu, the phase is your minus 90 because this is a constant throughout. Okay. So what we can see, phi at UGB, omega UGB, okay, UGB is equal to what? Minus 90. So what is phase margin? Phase margin is this 180 plus phi at omega UGB. So it is 180 minus 90, it is equal to 90 degree. So it is a maximum phase. So it is maximum phase margin possible for the first order system. If we increase the order of the system, then there is a possibility you will get a phase margin worst and worst. So ideally for the better stability, to avoid the ringing, we usually expect the phase margin somehow greater than 60 is acceptable or good phase margin. It is considered as a good phase margin for stability viewpoint. From stability point of view. Point of view. So what we can see, ideally, if the op amp is ideal, then what are the expectations for ideal op amp? For ideal op amp, we have seen that DC gain is infinite. It means your means DC gain is infinite, and UGB what you are getting is nothing but GMY. What is a C load or C out you are driving with the GM cell, and what we can see, the phase margin for the first order system ideally it should be 90 degree, or it's for the first order system it should be 90 degree. So it is a stable system. When you're using the closed loop system, it is a stable system. But what is the problem actually? So the problem with this transfer function associated with it, we ideally will not get the infinite gain. Any practical, any practical op amp has none, or can say has finite gain only. Okay. So any practical op amp has only finite gain. So but ideally we want it to be the infinite, but it is not possible actually. So what is the reason that it is not possible? Okay, so reason we will see. We will see that for any GM cell, what is the expected thing we have considered here? We have considered that there is no output impedance offered by this cell. But practically, there is some output impedance also, which I call R out for this GM cell, and there is also the capacitor which we are connecting as a load. Okay, yeah. So if we will now plot this V out, what we will see, there is a there is a infinite, there is a finite gain. Sorry, I should say there is a finite gain. Okay, yeah. So what you can see, the current again generated, let I call it I. I generated here is what? Again GM V in. So what is the V out here? V out is nothing but I by let I call conductance, which I call, or I not conductance, I will should say admittance. Instead of impedance, I will use the admittance. Okay. So two parallel means elements, the impedance will be what? G naught plus CLS. Okay. So what is this G naught? G naught is nothing but 1 upon R naught. And what is the R naught? Impedance offered by impedance offered by GM cell GM cell at its output. So ideally what we considered, the gain should be infinite, but here we will see that gain is not infinite. Okay, so what exactly it is? It is GM V in by G naught plus CLS. Okay, so what the transfer function comes from here? V out by V in S is equal to GM by G naught plus CLS. Okay, so in a different way, I can write it as GM by G naught divided by 1 plus CLS by G naught. Okay, so this is the transfer function when we consider a practical GM cell which has some output impedance. Okay, so for the practical GM cell, what is the transfer function that we have seen on the previous page? It is nothing but GM by G naught divided by 1 plus, okay, 1 plus CLS by G naught. Okay, so from here what we can see two things. Now DC gain is finite, which is GM by G naught, also we call GM R naught. Usually we like it, we write like this only for the GM cell, for the 5 transistor OTA structure. Okay, so what the 3D frequency? Previously it was 0 because pole was at origin. Now pole is not on the origin. It is what? It is G naught by CL, which I can also write 1 upon R naught CL. So for the first order system, this is the 3D frequency. Okay. Now what is the UGB? UGB is a multiplication of these two. So it is again GM by CL. Okay. It is nothing but multiplication of DC gain and 3 dB frequency. So what we can see from here, UGB is fixed. Okay. So when the system is practical or ideal, this UGB is fixed. UGB is same. Who is changed? 3 dB frequency is increased because there is a finite time constant because of finite time constant. Okay. And what is happened again? DC gain is reduced. DC gain is reduced. So what we expect now, we'll draw this Bode plot here. Okay, so let's see the Bode plot. So what I can see, your DC gain is somewhere like what is the value, which is GM R naught. It is some constant, and after that it is reducing with a slope of minus 20 dB per decade. And what is this value? This I call omega mu is equal to Gm by Cl, and this slope is minus 20 dB per decade. So it is a first order system whose pole is like that, and this is your nothing but what you call G naught by CL. Okay, so this is the plot, and what will happen? We can see on the phase plot. This is the omega in the log scale, and the phase plot. We'll see that phase is starting with this what I call 0, and at what I call at UGB, it is sorry, not UGB, at 3D frequency, it is reaching minus 45. Okay, so it is a minus 45, and after some value it reaches minus 90. When it crosses somehow nearly the UG frequency, it reaches minus 90. Okay, because we considered that this is omega mu, we have considered that omega mu is much greater than omega 3 dB. So the phase contributed by is nearly minus 90. We can also write for the phase of the system. Phase of the system is minus 90 omega by omega uh, 3 dB. Okay, so at UG what will happen, you will see that UGB is much greater than at omega equal to omega u, so it is much greater than the 3D frequency, so it will contribute nearly, this is nothing but this is the order of your gain. Okay, DC gain, so this thing will contribute nearly to the minus 90 degree. So from here what we can see, phase margin is again 180 plus this angle, which is nothing but minus 90, so it is of overall plus 90. So phase margin is still good, but ideally what we want maximum possible DC gain, which is infinite. So ideal integrator tells this thing. Okay, now we'll compare both the body plots. So actually ideally we wanted this as a body plot, so which is nothing but omega u is gm by cl. This is omega on scale. And what is happening for the practical circuit? Okay, so this is the ideal consideration, and for the practical, what is happening? This is your gm r naught. Okay, and what is this frequency? This frequency is nothing but 1 upon r naught cl, or I should say g naught by cl, and this thing I should say gm by g naught. Okay, so what will happen after this? After this frequency, it will follow this curve only. Okay, it will follow this curve only. So it means the UGB is same for the both the system. So your the practical system overlap this ideal system, that we can also see from this transfer function. So what was the transfer function for the ideal system was? It was nothing but Gm by CLS. And what is the transfer function for practical system? It is nothing but Gm by G naught plus 1 plus CLS by G naught. So what will happen at S equal to G naught by CL? What will happen at this frequency? Let's say. Okay, so at this frequency, if we put this frequency in this is for ideal, and this is for practical GM cell having output impedance R naught. Okay, for practical. So when we put this is coming from practical for S equal to G naught by CL, or I would say omega equal to this frequency. So S means omega I want. Okay, omega. So what will happen for the ideal system at omega equal to G naught by CL? What will happen? So it is Gm by CL at this omega, G naught by CL. So it is nothing but Gm by G naught. Okay, so this is the practical DC gain. So practical DC gain, yeah, it is a DC gain of your practical system. So what we can say, your ideal system is also, the DC gain of ideal system is also equal to DC gain of your practical system at this frequency. So it means these two plots will coincide here. Okay, so one plot was coming like this, so at this frequency this is like this, so they will coincide here. So this is the frequency called omega equal to 1 upon r naught cl for this first order system, or we can say for the ideal for the practical system. Okay, and after that both will follow and will reach to omega UGB. This is called GM by CM. Okay, so this is the discussion for the first order systems on the top level, or sorry, for the GM cell on the top level, where we have considered the practical aspect, because no GM cell is such that there is a no practical means output impedance. There is always output impedance. So what is our motivation? What is actually GM cell? Okay, so now, so ideally, what we want, ideally, we want infinite DC gain, for integrator or for op amp, because op amp is nothing but an integration. So why we want ideal gain? Why we want ideal gain is the point. Means why we want the infinite DC gain? Because in negative system, actually we want means no error. Ideally, what we want, okay, ideally if there is a op amp, what we want, this error voltage should be zero, and the output generated by what is what nothing but an integration of this error voltage, some constant omega mu and some k value. So when this error voltage is zero, we have some constant output voltage. If this error voltage is positive, okay, V out is positive and increasing. Okay, so still integration is happening. And if V out, if V is negative, and what is integration is happening in other direction. V out is integration is happening in other direction. Okay, so why we want infinite DC gain? Because we know in negative feedback system, if this is my input, we will see this thing later, and if there is a, this is my op amp whose gain is a, and it is used in the negative feedback system. So this is a factor beta. This is my error voltage. So what do you want? Error voltage what? This error voltage, we have to calculate the error voltage. Actually, what is V out? V out is in one sense A times V error. And what is this V error? V error is nothing but what do you call it? V in minus beta times V out. Okay. So what is the V out? V out is your AVA. So it is minus beta A VA. So let me take VE common on this side. 1 plus A beta equal to V. So what is this relative error? Means error with respect to your input voltages. 1 plus A beta inverse. Okay. So if I consider A beta, means which is called the loop gain, much greater than the 1. So when the loop gain is higher, what you can see, this relative error is nothing but 1 upon A beta. Okay. So higher this loop gain, uh, higher the loop gain is called A beta, better is performance, because error is minimized. Error is minimum. Okay, so error is minimum, then we can say it is performing in a better way. Ideally, there should be no error. Ideally, this error should be zero. It means what is the error? Actually, relative error is nothing but 1 upon A beta. So it is, let's say, infinite. It directly means A is infinite, because beta is some finite quantity. Beta is some finite quantity. So larger this loop gain means A is higher. So A is infinite means this relative error is what? Zero. So ideally what we want, there should not be any error. Okay. So in the two inputs, ideally they should be equal. There should not be any error for the amplifier. Okay. Or for the, so ideally the error should be zero. So it is a perfect integrator then. This is the definition of op amp. Okay, so that's why we want an infinite DC gain. But practically we cannot avoid this output impedance. So finally, in our design, what happens? So what is the GM cell actually? GM cell is nothing but it is a current source, that I can say. It is a current source. It's a current source only. I can also write it like this. GM cell is nothing but a current source. So what happens for a current source? If this is this output impedance, ideally we want it should be as large as possible, infinite for ideal current source. Okay, for ideal current source, the output impedance should be infinite. Okay, so this is also like that. This is the R out for the current source. So ideally it should be infinite. So GM cell is nothing but a current source. So ideally you want its output impedance should be infinite. So what we do when we design the op amp, we want that output impedance of output. What we want when we design the op amp, we want output impedance. This output impedance should be as high as possible, as high as possible, so that so that we can have ideal characteristics. Okay, so what we do in that sense, when we design the GM cell, we always want more and more output impedance. We always want more and more output impedance. So now we cannot get higher output impedance, much higher output impedance with a single GM cell, that is our 5 transistor OTA structure. We need some improvements. Now let come at the snapback of the 5 transistor OTA structure. What we see, what is the output impedance in general? What is the output impedance? It is not much higher. Okay, so it is not much higher. It is limited by some sort of upside impedance and downside impedance. So it is not ideal, we can say it is not infinite. Not infinite output impedance. So what we do? We choose different design methodologies. We choose different design methodologies to improve the output impedance. Output impedance. Because my GM cell is nothing but a current source which is generating a current here. So I want an infinite impedance ideally for the current source, or what maximum as possible, so that I can have the better gain response or better DC gain which is approaching to the infinite. And other thing, this means, okay, so it can be the better integrator. So for that, what we do, we choose different topologies or different methodologies, in which one is a cascoding. Okay, we use the cascoding to improve this R out. In this, we uses two structures: telescopic structure, telescopic structure. We also use folded cascode structure. So these are nothing but methods to improve your output impedance, to improve the gain. Okay, so ideally you want the infinite DC gain. So this is the few. I mean, these are the few points which I want to make here. Later we will see the exact frequency domain analysis in the design level. We will see the calculation of zeros and calculation of poles for this 5 transistor OTA structure. And before that, in one more video, I'll talk about the frequency response on top level. Then in further videos, we'll enter inside it, inside the, or we'll go at the transistor level. Okay, so this is, I think, enough for the for introducing you about the frequency response, why our decision should be infinite, and what the exactly ideal integrator means, what is the present op amp. So these are few points, and why this phase margin and why this phase margin is required. Okay, so I think this is enough for this video purpose. In the coming video, we'll exactly see how we can calculate the zeros and poles in the design level or at the top level. Okay, so thank you. With this, let you see in the coming video.